Is this on? Yeah. Okay, nice to see so many people here at the last hour. You're excited, and I'm tired, but yeah. This is the last talk. I won't hold you here for too long, but before we get started, I want to say thank you. I don't know if this is actually working. It is working, to the organizers for organizing this awesome conference. Also, this year is actually Chrome's 15-year anniversary. So, and I do work on the Chrome browser and standards. But the funny thing is that people reached out to me and asked, like, hey, do you want to be part of this like promotion thing? Like, we're asking people, what did you do when you were 15? And I'm probably a bit older than most of you, so I was like thinking, what did I actually do at that point? I looked back and I found I was actually playing around with Netscape. I just got Netscape. I had Mosaic before that. This is kind of like, this was my introduction to the web, and this is what got me hooked. This was so awesome. I was a major fanboy of Netscape at that point. Yeah, super cool. Since then, I joined a company. Some of you might remember them. Everyone knew us for a while. It was super cool, and then like everyone forgot about us. This is actually the original logo, if you've ever seen it. They also made rubber boots and rubber tires, and I think even paper. Yeah, it's a very old company. So basically, I worked on this phone called the Nokia N9. So I actually was leading the whole team doing the browser. This is why I moved back. I was living in Brazil, so I moved back to Denmark to work on this project. It was really cool. But then we got this guy, Steven Elop. He joined the company and said, oh no, it's all going to be my Windows phone, and we already have a browser. It's the best one. It's called Internet Explorer. So we don't really need you anymore. And well, that was kind of sad. So I ended up joining Intel. And that's why I'm here today. So my name is Kenneth Rohde Christiansen. I work for Intel, a semiconductor, where I'm a principal engineer. I've been working on web browsers for around 15 years. So yeah, it's been a while. I'm one of the co-authors of Progressive Web Apps. It's one of the things I've been promoting. I've been trying to promote people to build actual experiences on the web, always like go the extra mile. And yeah, I've been part of the technical architecture group as well in standardization. Yeah, if you want to follow me on this thing that used to be called Twitter, you can scan that, or you can just like type in my name. Anyway, the first question that people always have is like, Intel, you do chips, right? So what are you doing on the web? This makes absolutely no sense. But it actually does, because like, like everything runs on software today. Without software, it's just a dumb hardware. You can't use it for anything. And at Intel, we really value like openness, choice, and trust. So we work on a lot of different open source projects and standards. You might know some of them. You might have heard about Wi-Fi. I guess you know that. USB, PCIe, this Linux thing, yeah. And maybe you even heard about Chrome, Chromium Edge, and the Bytecode Alliance is about WebAssembly, if you didn't know. Yeah, cool. Give that guy a beer after this event. What I really love my company. I think it's really great. I have really good bosses. I think the company is really transparent and good at listening to the engineers, and they really value like sustainability, and it's really trying to improve. And that's something that's really close to my heart. So that's really cool to know. So why do we care about the web? Well, the thing is it's all about software, right? So we have these ecosystems, and well, you need to be able to create like awesome experiences on that and easy and with ease. And companies today, well, you're limited with money. You can't build a native Windows app, a native macOS app, a native iOS app, a native Android app, a native whatever app. Like that is just impossible. It's very expensive. You have to coordinate the backend to work across all these different platforms, the feature set. You need to find the skill set. It's kind of difficult. So what we're often seeing, especially on desktop, is that developers look towards the web. They want to be on the web. They want to be like a click away, like the advantage of the web. Just type in URL and there you are. And if they can build upon that and create an application that can work across many different platforms like Chrome OS, Windows, macOS, like that's a pretty good advantage. And we're seeing many do this. Sometimes the web is not up to task and you have to rely on a hybrid solution like Electron, but that's also fine. So the vision we have at Intel is to want the web to become this unquestionable key application platform, a platform that you can use for creating apps. At the same time, we don't want to ruin the web. We want to really strengthen all the things that makes the web great. Like everything is just a URL away and you can launch it. It's not like you have to wrap the web app into a zip file. Some people had that idea at some point. So we really want like instant loading website. We want to really preserve like privacy and security. So that's kind of our focus, and we're doing pretty well. That's like the amazing part. We're getting all these new APIs. Like I work on myself on like Web App Manifest and all of that, so you can install web apps today. So they look like native applications. There are a lot of, like we saw Philip today talking about all the new cool things coming to CSS. Super amazing. Something I've worked on myself, like with URL pattern, navigation API, view transition, that makes it really easy to create these experiences where you have different views. There's even something called a close watcher. So you probably know today you get this like dialogue up. It looks really nice, and there's a small X you don't notice. You click back on your phone, and suddenly, where am I? Damn, I went back. Oh no. We can solve that now on the web because there's an API that will solve that. At least allow developers to solve it. URL pattern, all this is really good for routing. And at Intel, we really focus on performance. Like we're hardware, it should be fast. So like relentless focus on performance, like WebAssembly, optimizations across the pipeline, native support for machine learning coming. I'm going to talk about that in a bit. And really cool is that we're trying to bring the web into our hardware roadmaps. So when we're going to release the new platforms, which like, what is the major target of this platform? Is it machine learning? Well, then we should have an API for machine learning. So we're really aligning there. And that's something we've been essential in with my team. So that's really, really cool. And I've been working on new capabilities, making the web more capable. We don't want the web that is just where everyone can make where there's certain APIs that don't matter to the general population, but they enable very compelling use cases. So there's, for instance, some APIs that enabled Photoshop on the web, but you might not need them on your site. That doesn't mean they shouldn't exist. So this is kind of like we also want the developers to be able to bet on the web. So that means that you need some kind of you need those to be able to develop these experiences with ease without having to always rely on a lot of big builders and frameworks where a lot of magic is hidden. We're trying to remove some of that slowly, so it becomes easier to target the platform more directly. Examples on this is like view transition navigation API. So you might not need a router in a couple of years. It might be very easy to build one yourself, one that you actually know how works. Also, like I talked about these APIs for diverse experiences, like. If I create like a Lego app where I can talk to my Lego thing and it uses Bluetooth, well, then I would need a Bluetooth API. Also want to be ready for what comes next. Philip also mentioned this in his talk today. A cool thing that has happened the last year is that the browsers went together and found out maybe we're not always going to have the same features, but developers having a lot of pain points. We got rid of Internet Explorer 11, but sometimes there are a few APIs that I can't really use because they're not supported widely. So let's ask developers, what are their major pain points? And let's agree upon that and create a subset of the web that we all support. And let's expand that every year. That is the interop process. It's part of what we call WPF, so the Web Platform Test. And I don't know if it's over now, but a while ago you could submit new things for next year. And then all the browsers will look at that and they will improve it, and the web just becomes more uniform. Really cool. But we're also doing really well. There's 17.4 million JavaScript developers last I checked. This is probably even more today. At Intel, we do look at telemetry. More than 65% of time is spent on the web, inside web browsers. If you then count enough time inside Electron app and all of that, this probably goes to 80%. It's pretty wild. So here's like this is like a bit of old data, but you see like the number one app on Windows is Chrome. That's a web browser, by the way. Edge, that is also a web browser. Firefox, yeah, also a web browser. Outlook, oh yeah, that's becoming a progressive web app on Windows, so also kind of web. Then you have other web browsers. Excel and Word, they're also becoming web apps. So yeah, it's pretty much web. This is why we need to really focus on web workloads when we design hardware and do all the software. So, I don't know, time flies, so maybe this is 3-4 years ago, Google had this idea that let's try to really focus on one of the pain points of developers, like those APIs that everyone wants but are not available, like file system API. I can't do Visual Studio Code because I can't talk to the file system. Can we fix those advanced capabilities? So they created this project they call Project Fugu, and Intel and Microsoft joined together with Samsung and Electron. Like, it's an open process, and we really try to solve all those major, bridge the gap between native apps and web apps. And I would say this has been a huge success. All the major holes have been plugged, and now we're looking at the long tail of things that we need to be fixed. So there's much better copy and paste today, much better APIs for it. We have frictionless access to local files that is done in a privacy-preserving manner, safe access to external hardware, Bluetooth, etc., USB. Great success. So here's some examples. So Visual Studio Code. This is actually very funny because I have a friend called Kenneth. He's also Danish, called Kenneth Rohde. He used to be the program manager on Visual Studio Code. And we had a discussion. And the discussion was like, I was like promoting progressive web apps. Like, why isn't it a progressive web app? Why are you using Electron? And he told me, well, there are two reasons. One reason was I don't have access to local files. Like, not doable. So they fixed that. So now you can go to vscode.dev and you can start editing local files. The second thing they're actually working on plugging now is they said, well, you might not believe so, but all the plugins we have, if you're coding in Python, we actually don't do the syntax highlighting ourselves. We actually normally call it out to CPython, and that will find the errors and give us all this extra intelligence in the IDE. But CPython, that's kind of a native app. So that's why we need this plugin system. So actually, to today, what Microsoft has done is they implemented WebAssembly. They implemented something called WebAssembly System Interfaces, now just changed the name to Standard Interfaces, which is like a POSIX extension to WebAssembly. They implemented that inside of this app. And then they modified like CPython to be compilable to WebAssembly plus these WAS extensions, and suddenly it just runs on the web. And now, of course, if you want to do that with Go, you have to go and modify Go to do that, and Microsoft is working on exactly doing that. So in the future, you will be able to run everything just as a progressive web app. And that's kind of amazing. Another app that people always told me, this is at least the one app we're never, ever, ever, ever going to see on the web. Photoshop. That is so advanced. Can't do it. Those, like, you can load files that are like 8 gigabytes in size. Like, how is that going to work on the web? Well, we kind of like, we got to the point where it was possible. We had WebAssembly, so they could take the existing code and take piece by piece and make it run on the web. It was really slow, so they needed multi-threading. So we worked together on adding threading support to WebAssembly. They were also using a lot a thing called SIMD. It stands for Single Instruction Multiple Data. I have an explanation later. It's basically like on modern processors, instead of saying one number times another number, you can do maybe that for 4 numbers at the same time as one instruction, or 8 numbers, depending on the width. By doing that, in one case, they had a 160 times speed up. That's like, whoa. But on average, it's like even like a 3 to 4 times speed up. That's amazing. That made it possible to actually run this on the web. For the whole, like having the whole file in memory, they had to implement some kind of swapping. And here, people created something called the Origin Private File System. So it's like a version of the file system API that has a few restrictions that makes it super fast. So it's not general purpose I/O. And the other thing is that it's private to your origin. So if you go into your file explorer, you won't find those files on the hard drive. It's like a hidden file. And by using that, they could use the hard drive for doing this swapping. And that made Photoshop possible on the web. Wrong direction. Another example, iRobot. Well, they're using Bluetooth to allow this. I forgot. I think it's called Root. So this is a tool for kids. I think it's a pen you can put in the middle, so you can configure it, and you can actually draw on paper and the like. And all of that is possible due to Bluetooth. And now Lego has something very, very similar. When we add those things to the web, we really need to talk about safety and privacy. These things are not without risk. People have this idea that native apps are super safe. That is actually not the case. Probably know that Windows was not designed for networking like other OSs, so they had to plug all these holes and kind of retrofit things. And the same thing is like kind of with native apps. It's like you just trust them because they're in an app store. And there's been a review. But like, there's not been a manual review of people have been reading the code. It's kind of like some tools that's looking a bit and trying, but there's a lot of things they can miss. And when you have the rights on native, you basically get right to everything. I can write to any file on the system. I can talk to the network. I can do whatever. I can find out if you have online printers on your local network, and I can share that all with my site. That's what native apps can do. We can't let that allow that on the web. One thing with native app is that you have a limited set because you need to install them. You don't want to install apps all the time. But during a day, during a week, you visit many, many websites. So if all websites suddenly had access to these things, that would be really, really scary. So we keep a lot of focus on figuring out how to do that. One example with Bluetooth is websites have no idea what Bluetooth devices are around you. The browser will, but not the website. When you click on something, we demand you to click on something to show a dialog. So it can't just do it on load. When you do that, it will show you a list of devices, and you can try to filter them. So like, I only want to talk to speakers, for instance. And only when you click on it, that site will be connected to that one device, and then we won't know about any of the other devices around you. But we're all constantly trying to innovate and find new ways of doing this. The current focus of Intel is thus on capabilities, making the web more capable for creating app-like experiences, and achieving like really near native performance. At Intel, we like to say no silicon left behind. And our team kind of say like no silicon left behind as the whole world is moving towards web-based experiences. So some of the things we've been working on is like WebAssembly. I talked about multi-thread support, SIMD support. We've been working a lot on WebGPU. So that's a new API for talking to the GPU. There's a new API called Web Neural Network for machine learning. We'll talk more about that in a bit. And something called compute pressure. So this is one of the examples of how we're doing optimizations at Intel. So when we try to bring SIMD, the single instruction multiple data, this is the example, like instead of plussing one number, I'm plussing like a vector, 2 vectors instead. This is what is called 128-bit. That's supported by most hardware today. So that's what we could agree upon in the standard. We have hardware that can do this of a bit size 512. But for instance, here, we can just by looking at the code, sometimes we can just manually at runtime modify this code and run it on a higher bit length. And just by doing that, you see in one case, it's 1.5 times faster. In every case, it's about like at least 20% faster. So this is one of the optimizations we've been doing. Another example, this happened a lot. It's very common that hardware today, chips, they have like native decoders and encoders for media, especially for video. And as you're doing like a video conferencing, it would be nice that it would use the hardware for decoding the video and not doing it on CPU, and the same as for encoding, because otherwise it's going to drain all your battery. It's fine, like YouTube works by default because there's maybe the native app can do this. So on the web, what people are doing is like, yeah, they were like doing what the browser supported natively, or they will take FFmpeg and convert it using WebAssembly and run it all on CPU. So we worked together with Google on creating an API called Web Codec that allows you to use those native codecs that are on the system, if they are on the system, if they're available. And that has been a great success. So basically, you can make sure that Zoom are using these APIs today. We also have like I don't know if you heard about how much you know about CPUs, but people often call it big little core or performance cores and efficiency cores. So that it means that the cores and the CPUs are not equal. Some are designed they're smaller and designed for efficiency. Other ones are designed for like utmost performance, but they will use more battery. So why use the high performance core for everything we're doing if it doesn't matter? So we went into Chrome and actually found all the different threads and looked at them and said like, oh yeah, this is display critical. You should do that on performance core. Oh, this is like a background thing. It doesn't really matter when you do it. Put that on efficiency core. And by doing that, we got like 100 plus milliwatt power saving on Windows. Other things like that would be really good for some of our hardware. Other cases, the IPC, that's inter-process communications. So because Chrome and browser, they are many different processes. They talk together, send messages. We try to minimize that. And that costs like a 10% power saving for video playback on Windows. So see, like just by doing this optimization, we bring you like more performing web apps and more battery life. WebGPU is something we've been really involved with. This has shipped on May the 2nd. So this is like you probably know that there used to be OpenGL. And OpenGL, people decided this is not the best API. OpenGL had this idea, the old way of doing like 3D graphics was that people didn't know how to 3D graphics, so people created an API that would track state. So it solves all the state for you. It's easier to use. But tracking state means that you have to do that on the CPU. So a lot of context switches from CPU to GPU to CPU. So they said a lot of workloads became like CPU bound. So as people doing like their own engine, like Unity for games, they really know what they're doing. So this was really bad for performing. So we got this new generation of 3D APIs like Vulkan, like Apple's Metal, and WebGPU is basically this for the web, done in a standard way where we even came up with a shader language that is uniform and will work across different platforms. Collaboration between Google, Microsoft, Apple, and others. And we have worked on bringing this to, for instance, TensorFlow, etc. But WebGPU is much more than graphics, because what is amazing about WebGPU that you couldn't do with WebGL is that you can also use this for compute. So GPUs normally have this called shaders. Normally they have a vertex shader, so we have a vertical triangle, you can work on every vertex, or it can be like per pixel, so there are different kind of shader types, but also compute shader. You can use these for compute. A lot of people use GPU actually for machine learning. So this you can also do on the web today. So Intel is the owner of the WebGPU backend for TensorFlow, for instance. So this is something we see that will much better performance. I don't know, apparently there's one case where it's slower, and that's probably just something we could fix. But in general, you see like, wow, there's actually one case that's more than 200% faster. So this is just by supporting WebGPU in TensorFlow. And now we can start doing all the optimization, so this is just gonna get better and better. Here's one example. I don't know if that is auto-playing. I'll try to click again. There you go. So this is actually WebGPU running and doing stable diffusion on the client, not talking to the cloud at all. And that is just on a system. So all of these things are doable with WebGPU on the web. To understand machine learning, people have this idea that there's like bad hardware and there's great hardware. It's not so simple. You can see a CPU, it's like very little latency, so if you just need to do something really fast, it's often the best solution. If you want to do something that has to be done constantly, like identifying where your eyes are in the video stream, then a discrete GPU is really good. It's a discrete, so it can get a lot of power, so it's really fast, but there's also a bit of like startup cost. So just for a simple calculation, it's not the best solution. An iGPU, that's an integrated GPU that sits right on the chip. So it's often maybe even sharing the memory, so they need to copy maybe from CPU to GPU. So that startup time is really good, but performance, it can't really scale because it's not using the same amount of power. On the other hand, you have this new thing called an NPU, it's a neural processing unit, or Google call it a tensor processing unit, different name, same thing. That is really fast and good, but it's not the best performance. But it's very cheap. It uses almost no battery. So in some cases, like you just want to do background blowing, that's definitely what you want to use, right? But AI can also be integrated in existing APIs where you don't need to deal with it. Like we could do automatically, let's say, just turn on background blurring on my video stream and just do that on hardware. Or do face detection, do eye gaze correction, lighting correction, all of this without you having to do anything. So this brings us to a new API we bring to the web called Web Neural Network API. So at Intel, so I said like I was really proud that this is an official slide from Intel launching one of our chipsets, and they put a web API on the slide. It's like, wow, this is the first time this has ever happened. We also got a really, like you see Microsoft talking really well about this new API we are building, and you're going to hear a lot more about this when we're going to ship it. So why do we want native machine learning on the web? Well, first of all, I don't want the web to be left behind. I don't want everyone to have to move to native in order to be able to deal with this, or run everything on the cloud, which can be really expensive for you. Sometimes it's better as running Lower latency on the client, less cost for developers because you don't have to pay for all the cloud processing. That's kind of cool. So this is really, and of course, like this is going to enable a lot of new use cases that you never thought about before. Some examples of WebNN. Let's just zoom in. This is the existing performance of using this mobile net. It's just one. When we optimized that and started using the simple structured multi-data and threaded, we got like 3 times faster. But it's still like compared to native, pretty slow. But using WebNN, you see it is almost the same speed as native with this new API. So WebNN is like a really low-level API, probably not something you're going to code. This is something that TensorFlow or Onyx or all these upcoming machine learning APIs is going to use as an implementation detail. A bit like WebGPU. Very few people are using WebGL or WebGPU directly. They're going to use something like Babylon.js or 3JS instead. So if you look at the options for machine learning on the web, we have WebAssembly only running on CPU, WebGPU only GPU. This upcoming thing can run on any kind of hardware, including this native hardware created for machine learning, such as an NPU. The API is very low level, not something you have to develop. For actual developers, you're probably going to use some libraries for image classification, object detection, background segmentation, or you're going one step further and going to use something like TensorFlow. So I have like one demo from one of my colleagues in China, in Shanghai, where it's going to show you this API running. So it's showing like background blurring and then video segmentation. I hope you can understand this a bit. The voice is not so good. Oh, there's no sound on, sorry. Yeah, so let me just try to go through it. So the first thing he's trying is that he's turning on background blurring, and he's going to do that with WebAssembly and then with WebNN, and we're going to see the difference in performance. So this is still with an early implementation. So here you have like with SIMD, so that's even optimized with the single structure multiple data, and here you have WebNN. So in this case, you see the frame rate, it's a bit above 60 on a laptop, and this is the inference time, the time to run the model, the data against the model. And now he should, there's pretty good data there. Now we change to use WebNN instead. And you see how quickly you have more than twice, or at least like twice, or sometimes less. But it's pretty good, much better frame rate. And you see the time to do the inference is much better. So it's like 2.3 times faster, just by moving to this API. The other example is background segmentation. So let's see if he's changed this. So we'll stop this. And we go full screen. Background segmentation is to find out where is the head and what's the background. And let's modify that so we can change it with something else. So here you see the same thing running on SIMD. And then he's using this deep lab module. And that you see that's way slower. This is too slow. This is a better segmentation model. But then it's a bit slow. But then changing it to use WebNN instead, you see suddenly you get like a 4 times speed up. Much, much better. Something else we've been working on is compute pressure. So compute pressure, this is an API I've been working on. So you probably know like Netflix, if you're watching a stream, it adapts to the network bandwidth. So if you have a good bandwidth, you get like 4K. But instead of then like starting like just showing a few frames, when the network is bad, you just change the resolution and you can still watch it and enjoy it. But that's kind of the same, that's a limit of bandwidth. But many systems also have a limit on like the CPU processing power or GPU processing power or memory, etc. So maybe if you have like the system is running 100% and it's getting really hot and it's starting to throttle, maybe it's better that the app would know and say like, okay, I'm gonna turn off some of the fancy features. I'm gonna maybe change the resolution. So we've been working on an API to do exactly that. It's been quite difficult because it's global state. Global state means that you can often use it for side channel attacks. We actually proved that's possible, and then we fixed it by using mitigations. And also having this API that has the right balance between, so you can't use it for tracking, and it's not annoying users by asking the question, do you want to use this API? They have no idea what it's doing. Very simple API. There's 4 different states. Nominal, system's almost not doing anything. Fair, it's doing something. Now it's serious, it's getting close to the limits. Maybe you should not keep on adding new fancy features. And critical, now it's probably time that you should maybe consider doing something less, or if you can. Otherwise, the system might start throttling, and you might experience a very bad user experience. So here's a small demo I created. So I create this like nice widget of emoji that will show you how the system is doing. And I have this Mandelbrot generator that is using workers. So every time I add more workers, it will speed up, but it will also add more pressure to the system. So you see, oh, now it's into serious pressure on my little laptop. And if I keep on adding, it goes into a bad state. And similarly, if I stop, it should pretty quickly, the system is dealing with it really nicely. So you can see you can go up and down. So that's like a small example of how this API would work. So this is actually ongoing in the Origin trial right now. We have a lot of different people actually using it, experimenting with it, like Microsoft for Excel, apparently. There's Zoom, Slack, Whereby, there's Jitsi. So a lot of these companies working with the video conferencing are very, very excited about this API. But Microsoft actually had this very nice use case that they had this problem on Excel, online, that sometimes there's like other websites or other apps in the background making it really slow. So input latency is really bad. So if that happens, they want to like modify the UIs instead of like rendering everything. They use like some skeleton rendering, because like it's really important that you can actually type and something happens, and not that you type and then suddenly you see a long string. But we also been working on many, many other things. So especially media. So, you know, like Corona, COVID. You see, like Google Meet got 30 times increase in daily usage during this time. So everyone started focusing on media, and so did we. So we've been working with Teams and Meet. Like now you get 20% longer battery life using these apps. YouTube is like the same power and performance as the native app. That's pretty good. And Zoom, by using something like web codec, they got like a 75% video code latency reduction, much, much better. So here's like an example of how we work together with Zoom on identifying how to get better low latency, how to get more battery life, how to get more smoothness and connectivity, and how that kind of maps to some of these standards we've been working on. We also asked, like, what do the developers need? What do you need, Zoom? What does Whereby need? Like, they were kind of like automatic, native supported background blurring, face detection, and all of that. And we've been working on this. So here's one example of background blurring. So this is my colleague Eero showing that. So see that it works really well. So that is just using the native hardware of the system. And the API, very simple, basically just like say, oh, I need this. I don't know if this is the final API. There's always like a bit like how trying to find the right API. I think they wanted to end up with having 2 different levels of background blurring, like heavy blurring and not so heavy blurring. And in this example, you can see this is Chrome without the feature. This is the amount of power it's using. This is with our proposal, just a little bit less. If you're using something like TensorFlow, wow, it's more than 2.5 times the power usage. The same with Google's system called MediaPipe, which they're using on Google Meet. So another example here with OpenCV. That's the first thing we brought to the web with WebAssembly. 8 megabyte too big. Google, they managed to do something similar. Their own much smaller, 2 megabytes, still pretty large. And now we're bringing that to WebRTC itself. Another example. So this is about tracking the user, and it can even track like multiple people. So you see Eero is joining again, and you should see him tracking 2 people. Also like very simple API, basically say, hey, I want face detection, bounding box. We want to improve this, so the idea is that we could do something more detailed, like where's the eyes, where the nose, if we can do that in hardware, so you can do like funny faces and all of that. Same thing much faster than using something based on WebAssembly. We also brought these APIs to the web where you could. A lot of cameras actually support like hardware-based zoom, pin and tilt. So we added that to the web. But now we're just doing it automatically. So we have new APIs. We just say like track whoever's in the picture and just do it automatically. We're even having some ideas or some prototypes around like changing by modifying the eyes so it looks like you're looking in the camera. I don't know if that's nice, but let's see if we're shipping. We also added like all these knobs like exposure time, and now the same thing. Like why not just do that automatically? Say hey, do whatever you can. Maybe use machine learning. Really cool. One last thing. Now I've shown you all kinds of cool new APIs coming to the web. And as I really like promoting my team and our cool engineers, here I have like my friend Alexis showing you support he's working on for foldable displays. Unfortunately, we don't have any sound, so I have to go over this. So this is actually a foldable display. So this is actually a keyboard that's on top of the display. And now he's explaining exactly how it works, so I'm probably not gonna know exactly what he's thinking. But the idea is that you have this app, so you see like this is the small app, you click on it, it's gonna show the photo in the middle. That's really nice. But if you don't have that keyboard there, you don't really want the photo in the middle because it's bended here. You kind of maybe would want it at the top instead. So this is kind of the experience we don't want. So we've been working on multiple APIs, one that tells how it's folded, another one that tells you where is the fold. There's a fold here, now it's in folded mode. So he has a different version of the browser, which he patches on. So now if he clicks, now you see the whole viewport, and there's the top part, and then you have the fold. And then you have the spot. Also because like for touch, it's not really good at that folded area because of the display technology. So now with that modification, the website will know that's the top area and can show the photo there. Similarly, if you flip it around, I think that's what he's been doing right now, then maybe you could do a different kind of UI. Like here, like you show the picture on the other side with more information. So this gives you all kinds of new abilities as these kind of foldable devices become more readily available to developers. And there's actually he also created this very nice game, syncing ship game. And it's really cool. Like I think he had one demo where you could have it as a tent mode, so you could play against each other on both sides. He's not showing that in this demo. But it's similarly, he will show you how this works. I don't know, like he speaks more than I speak, so. But now you'll see, you can show a whole different UI. And now you'll just show it in the middle here. You'll show all that. It's not something you have to interact with, so just use it for showing data. Very cool. There's one additional demo, so this is the very last. Where he shows you some kind of a newspaper. So this is a newspaper. This is like how it normally is. But if you use it like in book mode, you can kind of use it like a traditional newspaper. So you see, you have like two different sides. So you see like these new APIs, they allow like all kinds of new cool options. Oh, this is actually pretty cool. You can fold it out and you can use it as a stand and as like a real computer. And here's just like a regular website, Many cool options with these new APIs. So, with that said, you see at Intel we're really working on empowering the web and future experiences and making sure that you can bet on the web for your future application needs. And with that said, I want to say thank you very much for listening to me and hope you had a good time.
And we have some time for questions. Raise your hand.
Thank you so much for the great talk, Kenneth. Often we hear from the vendors they are bringing this feature, for example, Zoom and Google Meet, but we never knew that actually Intel is actually powering those So my question is more about like different chips. Like for example, in web, we know like all the vendors are actually working together now, as you mentioned, to bring the common capabilities. Is this APIs are also being adopted by other chip vendors, for example, like in the chip industry?
Yeah, so generally everything on the web should be widely supported, or there should be like a way to detect that it's not possible. Like the foldable display API is only on foldable displays, obviously. An example, a lot of this background blurring and all of that we're working on Windows, that is implemented using Windows Studio Effects. So that is a Microsoft Windows API that every platform vendor will go and make support for. So Qualcomm will have support for that on their hardware, Intel on ours, and we will just try to make the very, very best implementation of it on our hardware. And that's what everyone is doing. Of course, like with the compute pressure that I'm working on, it's a basic implementation that will work on any kind of hardware. That should work, but maybe in the future we're looking at maybe we can do something better on Intel because we have more telemetry on the chips. So you can imagine like, okay, it's this example. A process is at 100%. So normally what a process will do is it's going to raise the frequency to get work out of the way so that you free up work for other apps. But it could actually also do the opposite. If you want to optimize for battery usage, you could say, well, maybe I should lower the frequency so I'm using less battery and try to keep the performance or like the utilization of the CPU as close to 100% or maybe 90% as possible. So in that case, it wouldn't be good if we always just looked at the percentage of utilization, but that requires us to know all kinds of other signals. So that means that by default, there will be an implementation that works pretty well for everyone, but we have the option to go and do something better. But so does everyone else. But we are actually doing it because this is a strategy for us.
Thank you. One last question. Like now, developers have access to all these low-level APIs. Do you think there is a security threat? And if yes, like how the teams, like how different vendors are actually trying to protect the end users from being exposed to those security threats?
Well, no, I don't believe security threat. I actually believe the web is much more secure than native apps. Than native platforms because we have to deal with this. Like we can't kind of ignore it and say, oh no, it has been reviewed by an app store. No, we really need to solve it. And we go through so many reviews. Like I worked on compute pressure, so I had to go with our Intel security and privacy team and have them review it. And they give feedback. Then we go to the Google one because it's going to pass the Google review process as well and launch process. And they give us feedback. And that's fine and we're good. And then we go through the W3C process. We go to the privacy and interest group called the Ping. And there's people from Brave and Apple pointed out, well, it's global states, so maybe you can manipulate the states to go into those 4 different states. And then maybe you can use that for sending data. That's probably very difficult, but I actually went ahead and actually implemented that and came up with an algorithm. So maybe I could transfer I tried to transfer hello world. So often I transferred hell and then like it was garbage or sometimes hello and there was garbage. So I invented like new ways like maybe how do I change the bit stream to a realign? So maybe now I get hell and then world and then send the data again. And after maybe half an hour, I get hello world. So here the threat vector is that it's kind of funny. It's more like a privacy thing. So let's say that you're on a website called PornTube, and you don't want anyone to know about that. And PornTube is collaborating with this website called Facebook behind their back. So Facebook, they know you're logged in, and it knows how to send out. So it sends out, this is the ID of the person on this system. And then the other one is on incognito, maybe even on a different browser and on this website that they don't want anyone to know about. And they intercept that, this is the user, and they sell that maybe to Facebook. So now Facebook and PornTube can link that user together. And suddenly when you're on Facebook, you get all kinds of ads you don't want to see. So that was like the threat vector. So something like, okay, that's kind of funny. So we actually found out that this is actually possible. On a system, it's really not practical. Like the system cannot do anything else. You basically don't want to run any one other app because then it's going to break. But in theory, it's possible. And for that reason, we found out ways to mitigate it. Like saying, there's so many data being sent, so hey, now you introduce a penalty. when people try to calibrate it, the states, well, we break that calibration. And with that in place, we could prove that now it's basically impossible to send with what we know today. And that was then presented at W3C. It was presented to Brave and Apple, and everyone said like, "Wow, this is cool! Like, you fixed it. You can go ahead. It's approved by the ping." So that's what we do for all these things. Like, otherwise, it's not going to go through the launch process. Of course, maybe there are cases where we got something wrong, and then we're going to do whatever to fix it as soon as possible. But I think in general, we are much more safe than native apps. They don't go through these review processes.
Thank you.
Thank you. Any other question? Yay.
If I got it correctly, the APIs you presented are not supported by browsers yet, right? How long we should wait?
Well, like I presented different kind of APIs, like WebGPU is actually supported today. I am not sure if background blurring that already landed. If not, it's in an origin trial. The compute press is an origin trial, and the first quarter of next year we're trying to launch it, so it's going to ship. WebNN is going to launch at some point soon. It's going to probably launch with the CPU backend, and then later we're going to add like the GPU backend, and then later the NPU backend, so we can launch that in steps. But that's definitely on the way. I can't exactly say when it's going to be announced because that's going to be an event. But hey, you'll probably know about it. All these other APIs, we're looking with the tracking and things. Some of these are implemented, but we're going through the standardization process of finding the right API shape. But that's also something I would expect to launch like around next year at some point. So, I think there was another question in the back.
Yeah, thank you for your presentation. Did you think about that you can create new captcha on this? Yeah, because you can easily detect bots with back pressure API, because you can show, for example, some fractals for these bots and detect their capacity and decide this bot or user, and also protect against DDoS on L7.
I don't think I understood like all you said, but I thought you talked about like reusing compute pressure for detecting bots and stuff like that.
Yeah, it's about you not only can provide much better user experience by this API. You also like company collect information. If you have a lot of bots, you could collect information about back pressure and detect bots because they don't have a lot of resources, and use it like captcha because it's possible.
Yeah. We like with this API, we're always looking at these other use cases and whatever is possible. Like compute pressure right now is global state. The global state, so it might be affected by other websites. We're also looking at potentially looking at per process, so like your own process. So you can detect if something is going wrong on your website, or like maybe even use it for detecting in the wild when you're deploying new code to see if that is like resulting in more people going into a bad experience. And I know that I think Whereby right now they're using that to detect when the people are having like bad experiences, whether that is caused by something external or whether that's caused by CPU pressure.
Thank you.
Okay. If that is it, I want to say thank you very much for listening and for attending this great conference. And yeah, until next time.
Thank you.